actually a very small team. We just have 6 people, and it's largely held up by the Bonsol Collective, which is a group of companies and projects that are, contributing to Bonsol and building on top of Bonsol. And if you're doing anything related to ZK on Solana, we'd love to have you. So jumping right in, like, why do we care about ZK? So there are two very important properties from ZK. One is compression and the other is privacy. So privacy is very important, but we'll focus a bit more on compression for this presentation. So like, you just need to look at the diagram on the right to understand what compression is. So you have a constrained environment, which is to say there's limited resources like compute and memory, and you send a request to a larger network. That request can be something as simple as, just perform this very large computation for me and return the result. So you can see the network executes the computation and generates a proof, and the resultant proof are given back to the constrained environment. So it's worth mentioning, even though it's very basic, that the proof is important, because without the proof, you have no way of knowing if the network is lying to you about the result, right? So the large network, that's actually what Bonsol is. And the left side is just like a more formal explanation of, what it contains. So I have a very simple example here. It's written in Rust, but you don't need to know Rust to know what it's doing. Like, it's just reading a message from the environment, and it's iterating around it like 1,000,000 times, and it's repeatedly hashing that single message. And, and that's the return value, like the final hash, right? So when you write this program in Rust or any language and you run Bonsol build, you get a binary. That binary is executable by a RISC-0 ZKVM in this case. And you feed both the binary and the input into the ZKVM. And the result is, the result of the execution, as well as proof that the execution was done correctly. What I mentioned was a very simple algorithm, but you can have as complex code as you want in that loop. Like, I'm hashing something 1,000,000 times, but there's algorithmic complexity on the left, which is like the collapse conjecture. It's like a very simple step, but it's performed so many times, right? And you can also have design complexity, which is like a on-chain game. So there, your compute explodes not because of algorithmic complexity, but because your game loop in general is very complicated, because each turn you're doing tons of checks like cooldowns and movement and attacks and damage, everything. So, but the beautiful part about this is that your compute can be as large as possible. Like for the previous example, I have 1,000,000 iterations, but that can as easily be like 1,000,000,000 iterations. And once the proof is generated, the verification is in constant time. So you can accept the result of the computation by verifying once, which is like with 200K compute units, which is available on most constrained environments. So it's worth mentioning a little bit about ZKVMs. I won't go too much into detail because the next talk by Vineet from Jolt is actually like in-depth into ZKVMs. So I'll ask you to stick around for that. The thing we care about most is the part in orange. So similar to how for ED25519 or encryption, you don't really need to know how the digital signature algorithm works. You just need to know that you can sign and verify. It's the same for ZKVMs as well. You have a prover, which takes the binary and the input, and it generates the output and the proof. And then your verifier just takes the proof, the binary, verifies it, and accepts the result. It just returns a true or false. So the value from this is you write your program once, you build it, you deploy it, and then you can repeatedly keep calling it for different inputs and you get different outputs. So, like, why does this work, right? So in traditional ZK proofs, you write a program and you compile it to a circuit, and only that circuit can be verified by a verifier. So what ZKVMs do is they actually build a circuit for the entire virtual machine. So your program technically becomes an input for the virtual machine. This means you can write a program in any language and any kind of program as long as it's executable by the VM, and it will be ZK provable, right? So this is a nice segue into Bonsol. So Bonsol is everything outside
like the request cycle. So Bonsol controls like the entire request response life cycle for any zkVM. It's basically, this is all you need to know in order to use Bonsol. Like what does a prover do? What do you need to verify, right? So yeah, and yeah, I have a simple example of the Bonsol workflow. So you write your program, and then with Bonsol tooling, you can build it and deploy the binary to the Bonsol network. And Bonsol also provides you the on-chain programs to make the requests and to get back the response. And it also verifies the proof, right? So that way, from a developer's perspective, it's actually quite simple. Like you don't really need to worry about what algorithm it's using, how it's proving, what a ZK circuit is. You just need to know what your program is, build it and deploy it, and then you just make an on-chain call to, perform the execution and return the result. The result comes back from the network, and it consists of like the proof as well as like the actual result of the execution which you care about. The Bonsol on-chain program also takes care of verifying the proof for you, which means you just need to accept the result. You need to provide the callback. So Bonsol on-chain program will actually execute the callback, right? So yeah, a little bit about the Bonsol roadmap. The public beta is live right now. And yeah, we're targeting Q1 2026 for the alpha and the incentivized mainnet by Q3. But yeah, like anybody is welcome. There's like a few links to join our builders chat in Telegram and like to join the Bonsol collective as well. So yeah, there's also a few very good examples on Bonsol. So if you scan the QR code on the right, there's a perceptron network, which is a very heavy computation and proof for that. So yeah, that's it. Thank you so much.